Okay, back for more. Today we are going to talk about the principles of thermochemistry a little bit. We're going to talk about how you can measure heat, and we're going to do some heat calculations. So back to the beginning, principles of thermochemistry. Starting off heat and energy. Thermochemistry studies how heat, and anytime we talk about heat, we can substitute the symbol Q for heat energy. Heat flows between a system and its surroundings, so when we study it, we will talk about Q going between the system and its surroundings. System is what we will study, and surroundings is everything else. So the heat is involved when we are studying it in a physical or chemical change. And heat is the energy that is transferred from one substance to another. And temperature is how we measure the average kinetic energy of molecules in a substance. So heat and temperature are not the same thing. Temperature is a relative indication of energy, and just need to know that they're not the exact same thing. Internal energy is the total amount of energy in a substance. The term for that is enthalpy, and its symbol is a capital letter H. So you will see the capital letter H there, and it involves the heat and work involved. But physics, we will leave most of the work to that, even though we do some work in chemistry, pressure volume work done by gases. But here we're going to just focus on the heat. So usually Q and H will be pretty much the same for our purposes in this unit. Endothermic versus exothermic. Endothermic, if we're dealing with an endothermic process, that means again a physical or a chemical change. If it's endothermic, we know heat is absorbed from the surroundings. So it's brought in from the surroundings to the system. So the change in the enthalpy is going to be a positive change. So energy is taken in from the surroundings into the system. It's from the surroundings to the system. If it's an exothermic process, heat is released to the surroundings from the system. So that's a negative delta H. So energy is lost from the system. There's a couple of visuals there. Exothermic, you can see the arrows going away from the system. In that case, it looks like an Erlenmeyer flask. And so the system is the process going on inside the flask. So the arrows are going out away from the flask. And in the right-hand picture, the arrows are going towards the flask. So it's endothermic. Then we have our energy diagrams. On the right, we have an exothermic, which would be a negative delta H. And then we have an endothermic, which is a positive delta H. It's looking at where you're starting off versus where you're finishing up in terms of potential energy. You start and then you finish. Where your reactants start, where you end up. So we've already looked at these when we had our reactions unit, so nothing should be new there. All right, and of course the law of conservation of energy. Energy is neither created nor destroyed, but it can be transferred from one form to another. So an example is if you eat a Big Mac, that's chemical energy that is in the Big Mac, and then let's say you go and you go for a walk. that's transforming that into mechanical energy to do the walking, as well as heat energy that you give off as you burn those calories. Speaking of calories, when we measure heat, we do have to get some units out of the way here. Heat energy units, we have joules, which is the SI unit for heat energy. A joule stands for a kilogram times a meter squared per second squared. That would be more of the physics unit, or if you want to call it the force, I guess, analogy. And a joule, then it's I'm trying to think of the word for it. Its partner is also a calorie, another unit. You have the quantity of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. That's the definition of a calorie. And then you also have kilocalories, because a calorie is a really, really, really small unit of energy. And when they started measuring calories and realizing that people needed to pay attention to how much food that they were taking in and measuring that, I realized people couldn't keep track of that many of that small of a unit, so they created the food calorie. You notice that a small calorie has a lowercase c and a food calorie has a capital C. So you do have to pay attention to whether or not the C is capitalized on the calorie. One is a kilocalorie and one is not. So the equality there is a regular calorie is equal to 4.184 joules. And regular calories, if you have 1,000 of them, they're equal to 1 food calorie. So let's look at this sample problem, the first one. If you have 3,200 joules, so that's your given, and you want to convert those to regular calories. So joules have to go on the bottom, regular calories on the top, and 1 calorie is 4.184 joules. So we put that equality in, we divide, and we have 2 sig figs in the 3,200, 4 in the 4.184, and so we get 760 calories. The next one, we have 6.5 food calories, and we know 1 food calorie is equal to 1,000 regular calories. And we know 1 regular calorie is equal to 4.184 joules. And this would be 27,000 joules. And that's because 6.5 has 2 sig figs. Alrighty. Moving on to the next page, heat calculations. So when we're performing heat calculations, we're going to be using the formula Q equals mc delta T. And in this, Q again is measuring heat energy. That can be in joules or calories, depending on what the problem is giving it to you in or asking for it in. M is going to be representing mass, and that's going to be in grams. CP is the C, and that represents specific heat capacity. And that is a measure of the thermal energy needed to raise the temperature of 1 gram of a material by 1 degree Celsius. Basically, how much energy it takes to heat something up. And if it's something that's a good conductor of energy, it's going to have a low C value. And if it's a good insulator, it's going to have a high C value. Now, the units, I know I skipped over that, I shouldn't have. The units for specific heat capacity are going to be either joules per gram degree Celsius or calories per gram degree Celsius, because it's how much energy it takes to raise the temperature of 1 gram by 1 degree Celsius. So it's got a lot of stuff going on in there. If it's liquid water, it's got a specific heat of 4.184 joules per gram degree Celsius. and if it's in calories, it's 1.00. The delta T, remember delta stands for change, so this is the temperature change. So you're going to take the high value minus the low value. Unless they want to know if the Q is positive or negative, and if that's the case, then you always want to take final minus initial. So if you are expected to get a true positive or negative value for Q, you will then want to take final minus initial. All right, so let's look at some sample heat calculations here. How much heat, so if they're asking for heat, that's Q. So I know Q equals MC delta T, is absorbed by 500 grams of water as its temperatures increase from 14 to 75. So we're substituting Q equals M, which is 500 grams. C, well, water has a C value of 4.184 grams, joules, excuse me, per gram degrees Celsius. And the temperature change is 75 minus 14 degrees Celsius. So 75 minus 14 is 61 degrees Celsius. So I'm going to punch it in my calculator. 500 times 4.184 times 61. So 500 times 4.184 times 61. 500 has 3 sig figs, excuse me. 4.184 has 4 and 61 has 2. So I'm going to keep 2. Now when I do this, I get a big old number. And so I'm going to put this into scientific notation because I don't like how big the number is, because I get 121,612 joules. So with 2 sig figs, that's 130,000 joules, which I like 1.3 times 10 to the 5th joules. Or you could always say it's 130 kilojoules also, if you want to. All right, another one. A 75-gram piece of zinc was cooled from 115 degrees Celsius to 35 degrees Celsius. How many joules of heat must have been removed? So they're asking for joules of heat. Joules is a unit, so they don't ask specifically, but since joules is a unit of Q, then I know I'm solving for Q. So MC delta T. M is 75.0 grams. The C I'm using, since it's zinc, is 0.387. And 115 minus 35 is 80, with the terminal decimal there. Solve for Q, and I get 2 sig figs, 2,300 joules. All right, so here's a table with a bunch of specific heat values if you need them. Interesting to note, one of the higher values here is air. Think about it, puffy jackets. Use air because it keeps you warm, because air is a good insulator.